Welcome back, everyone. We're back into topic 2, the slippery slope of life. And so now that we have an idea of what cells are, we're going to get into a little bit of chemistry now. So we're going to start out with how are chemical bonds formed in part 6 of our topic 2. So we have two objectives in this video. So by the end of this video, you should be able to describe the relationship between atoms and their chemical bonds, as well as explain the difference between hydrogen bonds, ionic bonds, and covalent bonds. So let's start out with a little bit of review. So we talked about earlier in topic 1 that life is made of matter. And if you recall, basically matter is any substance that occurs in space and has mass. So we also talked about elements. So elements are unique forms of matter with specific chemical or physical properties that cannot break down into smaller substances by ordinary chemical reactions. So think of the periodic table, and on that periodic table there's basically all the elements that have been discovered in nature as well as have been produced in the lab. So things like carbon or oxygen or hydrogen, nitrogen, those are all examples of elements. So I cannot take an atom of oxygen and break it down into a smaller substance. Okay, so I can't break it down into something else by ordinary chemical reactions. So oxygen, a single atom of oxygen has a specific chemical property and a physical property that is different from a carbon atom, for example. So elements are unique forms of matter. They each have specific chemical and physical properties. Now we already know what an atom is because we talked about it in our organization of life. So atoms are the smallest unit of matter that retains all of the elements' chemical properties. So I just talked about an atom of oxygen or an atom of carbon. So it's the smallest unit of matter. So when we talk about an atom is made of 3 parts. We have the nucleus that contains the protons and the neutrons. So you can see that the protons are positively charged and the neutrons are neutral charged. And then surrounding the nucleus we have the electrons. So the electrons are negatively charged. So those are the 3 subparticles that make up the atom. Okay? So in this case we have 2 protons. So I can tell you right now that the presence of these 2 protons can tell me right away what this element is. So this atom is helium because helium always has 2 protons. Okay? So this is an atom of helium. So just a reminder, protons and neutrons are always found in the nucleus of the atom. Whereas the electrons, since they're negatively charged, they're going to be orbiting the nucleus because of that negative charge kind of, is opposed to that positive charge of the proton in the nucleus. Okay. And then another thing to notice from this chart is the atomic mass unit, which is just, how we measure the mass of the object. Protons and neutrons have mass, but electrons, their mass is so small it's negligible. Okay, so when we look at, like, for example, this example is of this atom here has just 1 proton. So let's say it's hydrogen because hydrogen just has 1 proton, and we know that the mass protons have an AMU or mass of 1, and neutrons have an AMU mass of 1. So this particular atom of hydrogen would have an AMU of 2, okay, because it has 1 proton and 1 neutron. Okay, so we add that together, and the mass is found in the nucleus. but we would not count the mass of the electron because its mass is so small, it's so minute, we wouldn't count it. All right, so now let's get into some descriptions that will help us when we're looking at the periodic table. So we're going to talk about the atomic number and the atomic mass. So the atomic number of an element is determined by the number of protons. Okay, so for example, hydrogen, as I said before, has 1 proton. So its atomic number is 1. Helium has 2 protons, so its atomic number is 2. Oxygen has 8 protons, so its atomic number is 8. So the number of protons determines the element. Okay, so the atomic number is the number of protons. And that atomic number never changes for that element. So oxygen will always have 8 protons. It will never have 9. It will never have 7. Okay, so it will always have 8 protons. If it has 7 protons and not 8, it's not oxygen. It's nitrogen. Okay, so the atomic number is the number of protons, and that never changes. However, the number of neutrons in the nucleus of the atom can change and is variable for that element. So for example, if we have, for example, take a look down here, we might have chlorine, which always has 17 protons, so its atomic number is 17. But the number of neutrons in the nucleus can vary. So it could have 18 neutrons, it could have 20 neutrons. So that can vary. So when we have a number of neutrons vary in an element, we call the variations between the neutrons elements the isotopes. So the number of neutrons is variable, resulting in isotopes. All right. And then we have the mass number. So the mass number is the number of protons plus neutrons. So if I have 17 protons plus 18 neutrons, I add them together, I get 35 for that particular atom of chlorine. Okay, notice we don't add the electrons because, again, electrons have such minute mass that we don't count it. Okay, so for this particular atom of chlorine, its mass number is 35. But for this chlorine, it has 17 protons and 20 neutrons. So its mass number is 37. Okay, so mass number is simply adding up the protons and neutrons for that particular atom. So mass number is different from atomic mass. So atomic mass is calculating the mean mass number for its naturally occurring isotopes. So when I add up all of the naturally occurring isotopes of chlorine, I get it averaged out to about 35.45. So when I look at the periodic table, and I'll show you that in a minute, I will see that its atomic mass is always, a little different from just simply adding up the number of protons and neutrons. So it's adding in all the naturally occurring isotopes. And just by looking at this number, I can tell that most of the naturally occurring chlorine ion atoms here are probably like that, right? So because of this number. So there's probably not very many chlorine 37s out there. Okay, so atomic mass is the mean mass number for all the naturally occurring isotopes, whereas the mass number is for a particular atom, the number of protons and neutrons. Okay. So again, what are isotopes? Isotopes are just different forms of an element that have the same number of protons, but different number of neutrons. So for example, if we have, you can see here, we can do carbon dating. So carbon dating, we can actually look at how old something is that's been there based on the amount of carbon 14 to carbon 12. And so, because we know that carbon-14 is like a little radioisotope, and radioactive isotopes, they do emit neutrons and protons and electrons, and they kind of emit that in order to attain a more stable atomic configuration. So basically they will go from like, a more stable form, so they will perhaps go from carbon-14, which has 2 extra neutrons, to carbon-12. So they will emit those 2 extra neutrons to go to a more stable state. And in doing so, the removal of those neutrons, it takes time, okay? So depending on how much time it takes for that to be emitted, we can calculate that, and then that way we can kind of determine, what the half-life is, so how long it takes for that to occur. And then that way we can kind of compare it to, how much should be in a living organism today versus in the bones of something in the past, and date it that way. So radioisotopes are just radioactive isotopes. And then isotopes are just elements that have different numbers of neutrons compared to the protons. All right, so let's take a closer look at the periodic table. So this way we can actually kind of understand what we've been talking about, okay? So if we look at this periodic table, basically all of these are a bunch of these are naturally occurring elements on our Earth. Some of them are elements that we've been able to create in the lab but are not naturally occurring. So of course, for the purposes of biology, basically we just look at like the ones up here because these are the ones that are common in nature, or living things, I should say. We don't really see a lot of them, a lot of the ones down here in anything living. That's more like geology and stuff. Okay, so one thing you'll notice when we look at these is the way that they're grouped. So you can see we have like group number 1, group number 2, 3, 4, 5, 6, and then 13, 14, 15, 16, 18. So we'll talk more about this grouping in a little bit. Another thing you'll notice is if we look at the individual box. So let's look at, for example, hydrogen, number 1. So hydrogen's atomic number is 1. So right away, I know how many protons it has. It has 1. Just like nitrogen has 7, its atomic number is 7, so I know it has 7 protons. Sulfur, its atomic number is 16, so I know it has 16 protons. Okay. We have the symbol. So a lot of these you might not know right off the bat what it means. Okay, so like K, some of you might know what K stands for, but some of you might not, and that's okay. Sometimes they do give you the name underneath, so you can see it's potassium. So they do give you the name sometimes. Sometimes it's so small that you can't really read it. Usually over time, for the ones that are for biology, you just kind of memorize, because, just off the top of my head, we use a lot of hydrogen. We sodium, potassium, calcium, magnesium, helium. Those are the kind of the common ones. These guys over here are common. So I right away know what the symbols are. And then finally we have the atomic mass. So remember, the atomic mass is just basically the mass number of, the average mass number of all the commonly occurring elements, isotopes. So you can see that the atomic mass for hydrogen is just barely over 1. So basically, hydrogen is basically just a proton. That's about it. Okay? So we can kind of see what the different elements look like. All right? We'll go more into how to read this when we get into like the chemical bonds. Okay? So I'll probably go back to this in a minute. But let's do some review questions. So this review question, magnesium has an atomic number of 12. Which of the following statements is true of a neutral magnesium atom? Is it has 12 protons, 12 electrons, and 12 neutrons? Or is it has 12 protons, 12 electrons, and 6 neutrons? Or is it has 6 protons, 6 electrons, and no neutrons? Or is it has 6 protons, 6 electrons, and 6 neutrons? So remember, this is a neutral magnesium atom. So right off the bat, we know that the atomic number is 12. So that equals the number of protons. So right away I can, these two at the bottom are wrong. So it's between these two. So now we can see that it's a neutral atom. So that means that the positive and the negative are equal. So that means it has equal number of electrons to protons. And then if it's equal numbers for everything, then it means that it has 12 neutrons as well. So this is the correct answer. It has 12, 12, and 12 of everything. All right, here's another question. An isotope of sodium has a mass number of 22. How many neutrons does it have? Would it be 11, 12, 22, or 44? So the mass number is 22. So we have to take a look. Remember, mass number is the number of protons plus the number of neutrons. So we have to figure out, first of all, how many protons it has by looking at its atomic number. So sodium is Na. It has 11. So that's the number of protons. So we now know what the number of neutrons is, right? So 22 minus 11 is 11. Okay, so that's the answer. All right, so now that we know how to read a periodic table, we're going to use it to help us figure out how the likelihood that certain elements will bond together. So we already know in our life's organization hierarchy that when we have two or more atoms, that chemically bond together, they form something called a molecule. And in this case, when the atoms come together, it's their electrons that come together first. So we're going to talk about what's called the electron shells. So we talked about already that, let me get out a pen. So we already talked about how we have the nucleus of the atom and then we have the electrons circling it. So if we have electrons circling it, they are in a certain way. So they are in what we call electron shells. So the innermost shell has a maximum of 2 electrons. Okay, so let's say we are talking about hydrogen. So hydrogen, it has just 1 electron because it has 1 proton. Okay, so it will just have 1 electron circling its nucleus. Okay, helium over here, it has 2. Okay, so He, it will have 2 electrons circling its innermost shell because it only has 2. Now, let's talk about lithium. Lithium has 3 protons, so it will have 3 electrons if it's neutral. Now, if the first shell only holds 2, then that means there must be another electron shell. So the next electron shell can hold a maximum of 8 electrons. So when I'm talking about lithium, okay, there's the innermost shell holds 2 electrons, so there's 1, 2, and then the next shell holds a total of 8. So now we have 1 there, all right? So it has 7 more electrons that can fill its outermost shell, okay? If I talk about something like fluorine, Fluorine has nine protons. If it's neutral, then it would have 9 electrons. Okay, so its innermost shell gets filled first. So there's 2 of its electrons. Then comes the 7. 1, 2, 3, 4, 5, 6, 7. Okay, so it just needs 1 more to fill its shell. Okay. So, basically, this is where we talk about these electron shells, and we can see already that if we have something like lithium, it needs 7 more electrons to fill its outermost shell. And the octet rule states, with the exception of like these guys over here, that the innermost shell, atoms are more stable energetically when they have 8 electrons in their valence shell, the outermost shell. So fluorine here, look at fluorine. It has 7 of its 8 electrons. It just wants 1 more electron to fill its outermost shell. It really wants to be stable. Lithium, it needs 7 electrons. Most likely it's not going to get 7. So it would rather kind of get rid of this outermost electron and drop down to its more stable innermost shell. So this is where we get like chemical bonding occurs. So maybe the lithium and the fluorine kind of want to get together, where the lithium can kind of donate its electron and fluorine can kind of take that extra electron, something like that. So this is why we're talking about these electron shells. Okay, so figuring out how many electrons are in the outermost shell can help us figure out where the electrons, what the bonding type will be. Okay. All right, so another thing that we'll want to look at the periodic table is group number 18. So group number 18 are called noble gases. So noble gases are basically the ones that have their electron shells or outermost shells already filled. So for example, if we're talking about neon, or I'll do argon because then we can see the third shell filled. So argon has 18 protons, so it has 18 electrons. So it'll have 2 in its first innermost shell, and then it has 8 in its second shell. And then basically the more you go, you also get 8 in the third shell. All right, so it'll have 8 in its third shell. So its outermost shell is filled. So argon is a happy camper. Okay, its outermost shell is filled. So it's inert, meaning it's highly stable, it's non-reactive. It doesn't need to gain any more electrons, it doesn't need to lose any more electrons. So basically argon is happy, and so it's going to be non-reactive. So these guys right here are inert, noble gases. So they're not going to be reacting with anybody, they're just hanging out, okay? Whereas groups 1 through 17, these are more likely to form ions. So they're more likely to gain or lose their electrons to fill their outermost shells. Okay, so remember lithium probably wants, these guys over here probably want to lose electrons to drop down a shell. These guys over here want to gain electrons to fill their outermost shells. All right, so that way we can kind of figure out, their bonding. So these guys probably would like to bond with these guys over here. All right. So let's talk about chemical bonds and reactions. So not all elements have enough electrons, obviously, to fill their outermost shell. So most of them don't. So they're going to form chemical bonds. They're going to bond with each other to fill their shells. Okay. And so when they do bond together, they form a molecule. So here's an example. Okay, so we have sodium. Sodium, they have 11 protons, so they have 11 electrons. So here's 2 in the innermost shell, Here's 8 in the second shell, and so that's 10, and then they have this 1 electron in the third shell. Okay, this one lonely electron. So they'd rather get rid of it and drop down to the second shell to be more stable. Chlorine has 17 electrons, I think, I can't remember. So it has, 2 filled in the innermost, 8 filled in the next one, and then it has 7 filled in the next one, okay, the third. So it just has room for one more to be stable. So in this case, it would love to get that electron. So sodium would love to lose an electron, and chlorine would love to gain an electron. So they want to react together to form a molecule. Okay? So they want to be chemically bonded together to form a molecule. That way, they can, this one can lose an electron, this one can gain an electron. They can bond together. So let's talk about the different types of chemical bonds. So in your book, we'll go through them in order. So we're going to talk about ionic bonds, and then the covalent bonds, and then the hydrogen bonds. So the first one are ions and ionic bonds. So what I just talked about with the sodium and the chlorine, these are called forming ionic bonds. So when the sodium wants to lose an ion or electron, it wants to get rid of this extra electron. And when it does do that, it loses that electron. So when it loses an electron, it has one extra proton, 2 electrons. Okay, so one positive charge. Because it has, in this case, it has 11 protons, which are positive, but now it only has 10 electrons, which are negative. So it has a +1 charge. And since it has a +1 charge, it's now called an ion, specifically a cation, a positively charged ion, because it's lost an electron. Now chlorine has the opposite. Okay, so it has 17 protons, but now it has gained an extra electron, so it has 18 electrons. So it has a -1 charge. It's gained an extra electron. So it's called an anion. Okay, so it's gained an extra electron. It's an anion, a negatively charged ion. So when we are moving electrons from one atom to another, it's called an electron transfer, okay? And as these two are kind of donating electrons to each other, they form something called an ionic bond. So between ions of opposite charges. So now the sodium and the chlorine, they have formed an ionic bond. And if you know what sodium and chlorine together form, it's salt, okay? So it's a salt, table salt, actually. So this is different from covalent bonds. So covalent bonds, instead of donating electrons, they simply share the electrons between them, okay? So let me go back to the periodic table, and let's talk about carbon. So let me get my pen out. So carbon, carbon has 6 protons, okay? So 1, 2 electrons in its first shell, and then it has 4 electrons in its second shell. So that means it needs 4 electrons to fill its outermost shell. So it's really hard to lose 4 electrons or to gain electrons. So most likely it's not going to form ionic bonds with anybody. So it's going to want to share electrons with somebody, okay? So it's going to be sharing electrons instead. So it's going to go with the covalent bonds instead. So covalent bonds, they share electrons, okay? So here are a couple different types. So we can have something called I'll start with the nonpolar covalent bond. Non-polar covalent bond is when the electrons are shared equally between the two atoms, okay? So if we take a look at this example, remember carbon, in its outermost shell, it has 4 electrons. So I'm just going to draw outermost shell. So it has 4 electrons. Here's 1, here's 2, here's 3, here's 4. And it's bonding with hydrogen. And hydrogen has 1 electron in its outermost shell, right? So there's 1. 1. Sorry, it's hard to draw with a mouse. 1 and 1. So you can see how this carbon is going to form 4 covalent bonds, each with a different hydrogen atom. So this carbon is forming a hydrogen, a covalent bond with this hydrogen, where they're equally sharing each other's electrons. Okay, so that, these electrons are being shared between these, each equally shared between the two. Same with here, same with here, same with here. So that way, the hydrogen gets its 2 electrons, this guy gets its 2, this guy gets its 2, this guy gets the 2, to fill, their outermost shell, which is just 2. And then the carbon gets its 4 extra electrons to fill its outermost shell. Okay, so nonpolar is where they're equally sharing their electrons. Polar covalent bonds is basically the same thing, but it's unequally sharing the electrons. Okay, so in this case, we're going to talk about oxygen. So oxygen, its atomic number is 8. So instead of having 4 valence electrons, okay, it actually has 6 electrons in its outermost shell. Okay, so it's going to basically have 6 in its outermost shell. So it just needs 2 more. So it's going to want to form a bond with 2 hydrogens. Unfortunately, it's an unequal sharing. Okay, so the oxygen is going to kind of take a hold of the hydrogen's electrons more often. And because it's taking a hold of the electron more often, the electron is in the oxygen's orbit, the hydrogen's electrons in the oxygen's orbit more often, giving a slightly negative charge to this side of the water molecule. Okay, whereas since the electron is not really held in this side of the hydrogen very often, it gives this side of this molecule more of a positive charge. This side more of a positive charge. And so it forms a unequal sharing of electrons. Okay, so we end up with one side of the molecule ending up being slightly more negative than the other side. And so that's a polar covalent bond. So we have unequal sharing of electrons. So non-polar, we have equal sharing. Polar, we have unequal sharing. All right. And then this is just showing a double bond. Okay, so in this case, we have oxygen. Remember, oxygen has 6 valence electrons. 1, 2, 3, 4, 5, 6. So it's doing that twice. So it's sharing actually 4 electrons between each other. Okay, so it's a double bond. So instead of sharing 2 electrons, it's sharing 4. And it's equally sharing it with each other because it's oxygen, because it's nonpolar. All right, so that's just basically a covalent bond. So covalent bond, they're sharing the electrons. They're not gaining or losing electrons. They're sharing them. And then finally we get to hydrogen bonds. So hydrogen bonds are weak attractions or interactions between the slightly negative side of a nearby atom and a slightly positive side of a hydrogen atom. Okay, So if we recall from the polar covalent bond of a water molecule, remember the hydrogen side is slightly positive, and then the oxygen side is slightly negative. Okay, so since this side is slightly positive, it's going to be kind of attracted to the slightly negative end. And so this hydrogen atom on this oxygen, on this water molecule, is going to be slightly attracted to this oxygen end of this water molecule. And so they're going to form a weak bond called a hydrogen bond. Okay, so this bond is very weak, so it will break apart pretty easily. Okay, whereas the water molecule itself is held together by a covalent bond. Covalent bonds are strong bonds, okay, because they're, really sharing those electrons between them. So this is just a weak attraction. This is a strong bond. Okay, so this water molecule is held together. This is not going to break apart. But this hydrogen molecule is just going to form, or hydrogen atom is just going to form like a weak attraction to this oxygen end. Just a weak attraction, okay, to this nearby. And this, kind of explains liquid water. So basically, if you think of liquid water, it's just a bunch of water molecules, and they're just forming hydrogen bonds over and over again between themselves. So that's why it's liquid. They're forming and reforming hydrogen bonds over and over again with each other, forming this fluid. Okay. And then we don't really need to go into van der Waals interactions. They're just very weak interactions between molecules, in the sense that they have kind of a temporary charge that attracts the atoms that are very close together. Okay. I don't think your workbook goes into it, so we can kind of ignore it. Your textbook just briefly mentions it, which is why I put it in here. All right, so let's see if we can answer our review questions. So which type of bond represents a weak chemical bond? Hey, didn't I just talk about that? Is it A, polar covalent bond, B, a hydrogen bond, a C, covalent bond, or D, an ionic bond? So if you chose B, a hydrogen bond. So remember, hydrogen bonds are just weak attraction bonds to nearby molecules. The strongest bonds are covalent bonds, okay, because they're sharing the electrons, so they don't want to give them up. And then kind of the in-between would be an ionic bond. So the weakest would be hydrogen, weaker is ionic, strongest would be the covalent. It doesn't matter if we're talking polar or just a non-polar, they're both the same. All right, so we're done with, what are we? Oh, we're on part 7. I said part 6 earlier. So we're on part 7. How are chemical bonds formed? So by now you should be able to describe the relationship between atoms and their chemical bonds, as well as explain the difference between hydrogen bonds, ionic bonds, and covalent bonds. So next we're going to finish off the chapter with what are the properties of water. So focusing on how water molecules are held together with covalent bonds, but how they have attraction to each other with hydrogen bonds.